welcome to our today's webinar. Today, our speaker is Christiana Pantelidou from Trinity College, Dublin, and we are very happy of having her with ourselves today. Christiana, welcome, and she will gonna to talk about gravitational turbulence in large D. Okay, please.
Thank you. Let me start today's talk by thanking the organizers for inviting me to speak on this online seminar series on holography and applications of holography. Following their instructions today, I'd like to tell you a bit about a project I have recently been involved in collaboration with Thomas Andrade, Julian Sonner, and Benjamin Withers. Can you see my mouse? Excellent. And in this project, essentially, we studied gravitational turbulence in the large D limit of general relativity. And by gravitational turbulence, so gravitational turbulence refers to the development of turbulent dynamics in the context of gravitational physics. But before I move on to tell you more about this phenomenon and the details of the calculation that we did, let me start by reminding you a few basic things about traditional turbulence in fluids. Okay, so turbulence has actually been at the forefront of research in fluid mechanics for almost a century now. And this has been the case because it has been widely seen in nature in a variety of systems at a variety of scales. Say, for example, from a cup of tea to atmospheric dynamics, all the way to galaxy formation and beyond. So turbulence is everywhere around us. So it's just natural to want to get a better understanding of it. Now, the majority of the studies that have been done about turbulence in fluids focused on non-relativistic fluids, where the dynamics are essentially captured by the so-called Navier-Stokes equation. And one of the most fundamental conclusions that these studies reached was that turbulence is actually deeply rooted in the nonlinear structure of these equations. And just to emphasize this, here I'm giving you the Navier-Stokes equation for a non-relativistic incompressible fluid. So this is an equation that governs the dynamics of this fluid velocity field here. So it gives us its time evolution, if you want. And as you can see, this is just a schematic. On the right-hand side, we have a nonlinear term, okay? And it's precisely because of this nonlinear term that we have transfer of energy from one scale to the other, and eventually get the famous energy cascades in turbulence, okay? And because of this energy cascades, all the information of how we entered this turbulent regime to begin with, like for example, certain details about the initial conditions or details about the force that we're using to drive the system are completely erased. And what one is left is with some universal behavior in the sense of some power loss. And this, the first one to address this power loss was Kolmogorov with his theory of 1941. And I'll review this in a couple of slides. But given this nice and simple picture from fluid mechanics, and also the fact that Einstein equations are actually nonlinear, it's just natural to ask if turbulent dynamics can appear in gravity as well. Okay, but why would Einstein equations have anything to do with fluids? If you just take the equations and just stare at them, it's by far not obvious why the two should be related. But actually there is a long list of evidence that actually connect black hole horizons and fluids. And here I'm just listing only 3 such evidence, but the list is much longer than that. So the first such evidence goes back to Drumore in 1986, and it goes by the name membrane paradigm. And according to this paradigm, horizons actually behave as viscous membranes. Okay, that was the first link that was drawn. Later on, within the context of holography, we had various very interesting results, starting with the one by Polycastro, Son, Starnets, where they computed the shear viscosity from a black brane horizon. And since then, we have been able to construct, to calculate quite a few transport coefficients through horizons. And last but not least,
I have a very short, silly question. Membrane paradigm, I had the impression that it started out with Kip Thorne and Coworks, but that's not quite true, I guess.
My understanding is that Drumore was the one. I mean, I may be wrong. I wasn't born at that time, so.
Curiosity, yeah. It's
Okay.
all important. Just continue.
Yeah, sure.
Yes.
Yeah. And the last of the evidence that I wanted to quote on the slide is the very famous fluid gravity correspondence, which is an actual one-to-one map between near equilibrium black holes and solutions to viscous hydrodynamics. So the point I'm trying to take home here is that there is a very long list of evidence connecting the two. And this evidence are quite strong. So one may hope to see turbulence emerging in black hole dynamics. And in particular, one might hope to see universal features like the ones I was referencing on the previous slide that are typical for turbulent cascades in fluids. Okay, but so if you want, this is the main aim of this line of research. We want to construct turbulent black hole configurations and go and check if they have universal features. But of course, I need to be a bit more specific by what I mean when I'm saying universal features, like what power laws am I referring to and what observables. So in order to do that, I need to tell you a bit more about Kolmogorov's theory. Okay, so Kolmogorov introduced his theory in two very important papers that came out in 1941. And this is precisely why this theory sometimes is referred to as K41. So at the time when Kolmogorov started thinking about turbulence, it was clear from the literature at the time that the velocity field U is actually a random variable. Okay, so despite the fact that U, its dynamics is controlled from a deterministic equation, namely the Navier-Stokes equation, small changes in the initial data or other quantities in the system actually have a big effect on the velocity field. And it's in this sense that the velocity field U is actually a random variable. Okay. On the other hand, if one considers instead of the velocity field, its statistical properties, like, for example, the mean velocity field or some other correlation functions, these are actually simple and reproducible. So at that stage in the literature, it was natural for people to try to reformulate the Navier-Stokes equations in terms of these statistical properties. Okay, and people did that, but they soon realized that that was not the way out. And that was because these statistical evolution equations turned out to be unclosed. Okay, and what I mean by that is that they had more variables in these equations than equations to solve. Okay, and this issue of unclosure essentially came from the nonlinearities in the Navier-Stokes equation. That was the reason behind it. So the punchline here is that in order to make any progress, they had to make assumptions. And this is precisely what Kolmogorov did. So Kolmogorov focused on turbulence in 3+1 dimensions in non-relativistic fluids that were incompressible, and he made the following 3 assumptions. The first one typically goes by the name of isotropy hypothesis, and it essentially says that turbulent motion is statistically homogeneous and isotropic. Okay, this tremendously simplified the problem in the sense that it meant that the probability distribution function associated with this velocity field that was a random variable had to be translation and rotation invariant. Okay, then he moved on to make 2 more assumptions. These 2 assumptions are referred to as the similarity hypothesis. The first of which says that the statistics have to be to take a universal form that it's determined uniquely by 2 constants. These 2 constants are the viscosity that appears in the Navier-Stokes equations, and another constant that is referred to as the energy transfer rate and is denoted by epsilon. And essentially, the interpretation of this constant is the rate at which energy is transferred across scales. Okay, so the punchline of this hypothesis here is that the probability distribution function can only be a function of the viscosity and the energy transfer rate. And last but not least, he made 1 more assumption, which says that actually viscous effect only influence the very small scales. Okay, what this says is that there is a whole range called the inertial range, where the probability distribution function is actually only a function of the energy transfer rate, epsilon, and nothing else. Okay, so these are the assumptions that he made. And using this assumption, he went on to examine the following observables. So he was interested on a particular kind of endpoint functions of the velocity field in position space, namely the so-called longitudinal structure functions. Okay, these structure functions are calculated in this way that I write down here. So essentially, you take the velocity field at some point in your system X, and then you take the velocity field at some other point that is at a distance r from the original one. You take the difference between the 2, then you dot that with the unit vector along the line connecting the 2 points. You raise that to the power n. And then, of course, since, as I was saying on the previous slide, in turbulence, everything has to do with statistics, we need to take an appropriate statistical averaging. Okay, and by carrying out this process, one gets the nth longitudinal structure function, which is typically denoted by Sn. And remember, given that we made the assumption of the isotropy hypothesis, this quantity here can only depend on the separation between the 2 points, namely, it's only a function of r. So this is one of the observables that Kolmogorov was interested in. And then he was also interested at 1 more quantity, now in momentum space, that you might actually be a bit more familiar with, namely the energy power spectrum. This is typically denoted as E of k, and it's formally defined in this way here. But the punchline is that essentially the kinetic energy power spectrum measures how much kinetic energy you have in a shell of radius k in momentum space. Okay, so given the assumptions that we saw on the previous slide and the observables that he focused, Kolmogorov went on to formulate his theory about 3+1 turbulence. Okay, and essentially it boiled down to the fact that one has a direct energy cascade. So here is the picture. So here I'm plotting the kinetic energy power spectrum in momentum space on a log-log scale. And you should think of turbulence in 3+1 dimensions in the following way. Let's say we have a system and we pick a scale, say here, and we go and we introduce in the system just a few vortices, okay? What will happen because of the interactions and the nature of the interactions in 3 spatial dimensions, these vortices will now start breaking up into smaller and smaller ones, okay? So we see that we have a transfer of energy from large scales, the big vortices, to smaller and smaller ones. So in terms of momentum, we have transfer of energy from small k to larger k. So energy is moving from left to right on this plot. Okay, but if we keep evolving the system, eventually these vortices will become so small that will have the size of the dissipation scale. So they'll reach here. And because of dissipative effects, they'll be completely removed and the system will go back to equilibrium. Okay.
Sorry,
yeah?
I have a very elementary clarification question here. It's just probably me being confused. I thought the velocity distribution function, it needed to be isotropic, right? That was one of the assumptions.
Yes.
But when there exists some kind of vortices, they definitely break the symmetry along a particular direction, right?
Well, I mean, you take statistical averages, right?
Mm-hmm. So I'm not able to see how that would necessarily break the statistical symmetry, this rotational symmetry.
Well, we are, so do you understand why this quantity here is isotropic at the end of the day?
Yes, yes, of course. Mm-hmm.
Okay, so what, I'm not understanding the question then.
So okay, even in this case, for example, the vector y, is that also averaged over or no?
The vector u, you mean?
Y, the direction in which you take the correlation, the vector y, does that also have to be statistically averaged?
I mean, you statistically average the whole thing at the end.
Okay.
Maybe we can talk about it later. I'm not sure I understand. Sorry.
Yeah.
Okay.
I mean, just to interrupt Arvid, it's really a no-brainer, right? The individualizations may break rotational invariance, right? But when you average over all of them, you know, it has to become rotational invariant again. That's it, right? No magic.
I think so.
Yeah.
Thank you.
Okay, so I was here describing the direct cascade. So as I said, if we introduce a few vortices at this scale here, those will break into smaller, transferring energy at higher values of k, and eventually they will be removed from the system because of dissipation. So the system will go back to equilibrium. Okay, so how can we have a picture like this? Well, the answer is that you have to keep introducing vortices in your system. So we have to continuously introduce vortices at this forcing scale here. These vortices will continuously break into smaller and smaller ones, transferring energy to higher and higher scales. And then, of course, at the dissipation scale, small size vortices will continuously be removed. So we have a continuous cycle here. So we get a steady state. Okay, and what we see is that in between these two scales, where we have the inertial range, we see that the kinetic energy power spectrum actually exhibits a power law behavior. Remember, here we're on a log-log scale. Okay, and in particular, let me point out that this scaling law goes like k to the minus 5/3, and I'll come back to this in a couple of slides. And essentially, this comes from the fact that the only scale we have in this range is the rate at which energy is transferred from one scale to the other. Okay, so this is what happens in 3+1 dimensions. Let's now see what happens if we were in 2+1 dimensions. So what happens is that even though the picture that we get at the end of the day looks roughly similar to what we had before, the process is the opposite, in the sense that here we don't have a direct cascade, we have an inverse cascade. Okay, so what happens is the following. We pick a scale, and at that scale, we keep introducing vortices continuously in our system. Now, because of the nature of the interactions in two spatial directions, these vortices, instead of breaking into smaller ones, as we saw earlier in 3+1 dimensions, they will do the opposite. They'll come together to form bigger and bigger structures. So energy is transferred from small scales to larger scales. Or in terms of the momentum here, energy is transferred from large values of k to smaller values. Okay, so we have energy flowing from right to left in this picture. Now, if the system was infinite, this inertial range here would extend all the way. But for all practical purposes, the systems are never infinite. Okay, either because we're in the lab and we have a sample that has a finite size, or because we are doing numerical simulations and we can only simulate a finite size of grid points. So there will always be an IR cutoff here. And what precisely happens at that scale depends on what precisely we do. Now, in atmospheric physics, what people do is they go and they modify the Navier-Stokes equations to add friction terms. And these friction terms essentially take care of the large scale structures. Okay, what we'll do is, instead of that, we'll impose periodic boundary conditions on these two spatial dimensions. And we will effectively be solving our equations on finite volume. And what happens in that case is that there will be an accumulation of power at these very small values of k, which corresponds to a vortex lattice that is continuously fed from the UV. Okay, so once again, we see something similar as what we saw before. We have vortices coming in here, and then they continuously transfer energy to larger scales, and then they are sort of removed, or they condense at this scale. Okay, so we once again have a steady or quasi-steady state. Now, I said that here we have inverse cascade. Actually, that was not very precise. We also have a direct cascade that goes to higher momenta, but I will completely ignore it in this talk. So just forget about this point. Okay, so and once again, we see that in the inertial range, we have the kinetic energy power spectrum exhibiting a power law behavior, and the power is k to the minus 5/3. So it's exactly the same as the power that we had in 3+1 dimensions. And it turns out that this power is actually dimension independent. And the way to see that is very simple. It's just basically dimensional analysis. So let me walk you through it. So from the similarity hypothesis, we said that in the inertial range, the only parameter we can play with is this energy transfer rate epsilon, which by definition has dimensions of length to the square over time to the cube. Okay, so if we now turn our attention to the kinetic energy power spectrum, E of k, this has dimensions length to the cube over time square. And this should be expressible only in terms of this kinetic energy transfer rate epsilon, and also since it's a function of the momentum. But out of the two, only this epsilon has dimensions of time. So in order to, we start by taking care of this time to the power 2 using appropriate powers of epsilon. And it turns out that the right power is epsilon to the 2/3. And then we take care of the remaining length scale dimensions by appropriate powers of k. And it turns out that the right power is k to the -5/3. Okay, so this is the famous result by Kolmogorov that in the inertial range, the kinetic energy power spectrum should scale like k to the -5/3. And then the same argument goes through for the endpoint longitudinal structure function, which has dimensions length to the n over time to the n. This should be expressible in terms of epsilon, and this time the separation between the points that we considered, so r. Okay, and first, just like before, we take care of this time dimensions here by considering epsilon to the power n over 3, and we fix the remaining dimension using r. So it turns out that r should be raised to the power n over 3. So this is the famous result by Kolmogorov that the nth longitudinal structure function should scale like r to the n over 3 in the inertial range. So earlier, when I said that in this program, we want to go and construct turbulent black holes and check if they have universal features, this is precisely what I meant. We want to go and check if the energy power spectrum and the nth longitudinal structure function exhibit this scaling behavior. Okay. So having said that, now at the state to just very formally state what the aim in this project is. So we want to construct turbulent black brane configurations, and we want to check if they have a universal regime that is compatible with K4D1. And in particular, we will be interested in turbulent dynamics in 2+1 dimensions, which means that we want to focus on seeing inverse cascade. So this is our aim. And let me here outline that the approach that we're going to follow. So our starting point will be Einstein's equations, okay? And we want to solve these equations to ideally construct turbulent black branes in ADS4. Why ADS4? So we have the 2+1 dimensions that we want to see turbulence in, plus the radial direction. So 4 bulk dimensions in total. But unfortunately, this problem is technically very demanding. You have no symmetries, so all the components of the metric will be turned on. And not only they will turn on, but it will also depend on all 4 bulk dimensions. This in principle can be done, but given that this was a proof of concept computation, essentially, we wanted to have as much analytic control as we could. And this is precisely why we turned to the large D limit. Okay, so the large D limit not only simplified the equations that we wanted to solve substantially, but it also connected once again to fluids, which was good for us because it gave us the option of taking in intuition from fluid mechanics. Okay, and let me stress from the outset that we are doing large D. So in principle, these Einstein equations are in infinite number of dimensions, but we are restricting our dynamics down to 2+1 dimensions because that was what we wanted to do. We wanted to focus on inverse cascade in 2+1 dimensional turbulence. Okay, and of course, I tried to emphasize this before, but let me state it again a bit more clearly. So in doing this calculation, in order to be able to see the universal regime compatible with K4D1, we need to introduce a forcing term, okay? And this forcing term cannot be anything. It has to be something that is compatible with the isotropy hypothesis, okay? And if you want, this is a novelty of the calculation that we did. Okay.
Can I, Christiana, just a small question.
Sure.
Is it completely obvious that everything you just said is also correct in relativistic hydrodynamics? Is this completely obvious and somebody worked this out, or is there some reference? I mean, because Kolmogorov's theory is, very nicely non-relativistic. So I'm just curious about like the background to this.
Yes, so I think that's actually a very good question. So here I was very careful to say that our starting point is Einstein equations. And I said that because I wanted to distinguish from earlier work that other people did in gravitational turbulence, namely the Grubat perimeter, where what they did was actually to start from conformal hydrodynamics, do the calculation there, and then use the fluid gravity correspondent to actually go and make statements about black holes. Okay, as far as I know from the literature, that calculation, which was done in 2012, I think, was the first time when actually people looked at anything relativistic. Before that, it was all about non-relativistic fluids. And so, yeah, there is no, the literature is very limited when it comes to relativistic fluids. Did that answer?
Yes, but you expect all of these exponents and all these scalings to be the same somehow in relativistic hydrodynamics, right? This the energy cascade exponents and this.
We see.
You see them, right? Yeah. So,
we do see them.
Yeah.
But we are taking the large delimit. So, and when you take the large delimit, you essentially get a version, you get some equations that look like non-relativistic fluids. They're not exactly numbered.
Okay, so, thanks. Yeah, I was just asking, if you knew, say, in some reference in 1957, somebody used relativistic hydro to derive the same results as the K41 theory. Okay.
No, the scaling that I gave you is just dimensional analysis.
Yeah. No, I know.
But other than that, a more detailed study of relativistic fluids, I don't think has been done.
Okay, thanks.
Cool.
Christiana, another more historical question. Paul Chesler et al. I even got at some point a spectacular view graph about how the horizon looks like when you are in a turbulent regime, and it came from Paul Chesler, right? And Paul was quite busy with this in 2013. I had the impression.
Was it I thought it was 2014.
No,
I am gonna.
I was busy with it, and how does it relate? I think they didn't gravitationally back react, right? It's just the.
No, I think they did the full calculation. So they took Einstein equations in 4 bulk dimensions, and they solved them, and they got turbulent black holes. But they didn't manage to see K41. They saw something that one could maybe hope to look like, but it wasn't a clear K41. And the reason was because they did not have forcing. They entered the turbulent regime simply because of unstable initial conditions.
Yeah, I Googled very efficiently, and I have here their preprint. It's 2013, but it doesn't matter. And they say that this dimension, Kolmogorov dimension, is d+4/3. Right, and I guess that's the trouble you're referring to. This is better, right?
d+4/3. I'm not sure what.
This of Ladders 112, 2014, and it's in the abstract that they have the Kolmogorov dimension d+4/3.
I think you're referring to some fractal dimension that they mentioned, but I don't think that's widely accepted.
Kolmogorov is also fractal, right? It's simple, but.
But the calculation that they did was in ADS4.
Yeah, that's right.
Yeah.
Okay, just better, right? Just history.
Yeah. So the way that computation relates to what I'm doing here, first of all, that one is in finite D. What we are doing is in large D. And they did not have forcing, we do. because of precisely this distinction, they do not see K41, while we do. That's the comparison with Paul Chesler's work in a nutshell. Okay, so this was actually a very good point for you to ask questions, because I was just gonna move on into the more technical part now. But before I tell you the results that we obtain, let me just make sure that we are all on the same page on what the large delimit of gravity is. Okay, and I'll give a very quick hopefully three slide introduction to the main idea. Okay, so the main idea behind the large delimit of general relativity is to take the number of dimensions, d, and treat it as a parameter. And if you treat it as a parameter, then you can do a perturbative expansion in 1 over d as d becomes large. Now, why is this a good idea? Well, it turns out to be a good idea for black holes, because in black holes, in your system, you have two scales. You have the radius of the horizon, r0, and you have one more scale, r0 over d. And as d becomes large, there is a separation of scales between these two parameters. And whenever you see separation of scales, this hints towards the existence of an effective theory. Okay, and let me give you one argument where you see this separation of scales taking place explicitly. This has to do with considering fluctuations, and an interesting set of fluctuations, the most natural fluctuations one can consider, correspond to quasi-normal modes. Essentially, and here I'll be focusing on quasi-normal modes of the Schwarzschild ADS. Okay, and how do you compute these modes? So you take your equations, you fluctuate around your metric, you get a set of equations, and then you have to solve those subject to boundary conditions. On the horizon, as always, we impose regularity. And close to the boundary, we impose that the fall-off is fast enough. And if we do that at finite d, what we get is we get an infinite but discrete set of modes, omega n, that fill in this spectrum here. Okay. Now, if we now take the large delimit, what happens is that this spectrum will split into two sectors. On the one hand, we have the light sector, which includes just very few modes, the so-called light modes, which have frequencies of the order of 1 over r0. And we also have the so-called heavy sector, which includes all the remaining modes that are so-called heavy because they have frequencies that go like d over r0. Okay. So here we precisely see the two scales that I was quoting earlier. And we see that because d is taken to be large, we have a separation of scales. Okay. And actually this computation is very illuminating in the sense that it essentially hints towards how to obtain this effective theory. Well, if you just simply integrate out these heavy modes, you will be left with a theory that describes the dynamics of these light modes, which turn out to be localized close to the horizon. Okay. And okay, so this is the main idea. Let me just explain very briefly how to obtain this effective theory brute force. Okay, this was actually something that Ben taught me, so I think it's very interesting for everyone to know. So the procedure for getting this effective theory is the following. Our starting point is just like before, the ADS Schwarzschild metric, which here I collectively denote by G0. This is a function of the radial direction r. And as I said earlier, it depends on one constant, the radius of the horizon, or equivalently, the energy density, which I denote by A. Now, this is a black brane configuration, so we can just boost it, say by a momentum P. So we get a new metric that actually now depends on two constants, as well as the radial coordinate in ADS. Now, if we promote these two constants to functions of the boundary coordinates, so if we take A and P to be functions of T and X like here, we get a new metric, G0, that now not only depends on R, but it also depends on T and X. And if we take this and we plug it into Einstein equations, we'll see that the Einstein equations will not be satisfied anymore, but instead they will have an error of order 1 over D. And what we do next is to go back to this metric here and correct it by a term that goes like 1 over D in such a way to reduce the error in Einstein equations from 1 over D down to 1 over D squared. And one can keep going in this way by correcting the metric in powers of 1 over D in order to solve Einstein equations to higher and higher order. So in this way, we have essentially systematically solved a certain subset of Einstein equations, namely the evolution equations. And what we are left is with the so-called constraint equations. And the constraint equations I'm writing down here for you. So we have two such equations, one for the dynamics of the energy density and one for the dynamics of the momentum. And by the nature of this equation being constraint equations, they do not depend on R. Now, let me emphasize that we've done all the hard work analytically. And if we simply solve these two equations, we will land to full black hole metrics in ADS. Okay? Because we've already solved for the radial profile of the metric functions. Okay, so that was the first comment. The other comment that I sort of referred to earlier when I was talking to Sasso, these equations look very much like Navier-Stokes, and in particular incompressible Navier-Stokes equations, but they are not exactly the same in the sense that these equations are exact in gradients. So in the procedure that I described on the previous slide, I know where to did a gradient expansion. Okay, so these equations look like fluid, which is good for us because we can take intuition from fluid dynamics, but they are not, they do not rely on a gradient expansion. And it's in this sense that they're slightly under better control than hydrodynamics. And what I mean by this is the following. So in hydrodynamics, you do a derivative expansion, and then you have an infinite set of orders to solve for. But at the practical level, we cannot solve all those orders. So what we do is we truncate at some order. We treat those equations as being exact, and then we solve them. And if we solve them, we see that they have issues. They can be either acausal or ill-defined or unstable. So they have undesirable features. And then what we typically do is to go and modify these equations in order to remove these unwanted features. But what you're doing really is you're changing the microscopic theory. So here, we do not have to do any of this because our equations are exact in gradient. Okay.
Good question.
And, yes.
Christiana, is this one of the expansion asymptotic or converging? Is that clear?
The large D expansion, you mean?
Yeah. On the previous page, right? You rest on it, right? And it's like when it's a converging expansion, then you can pull it all the way to dimensions, but as asymptotic, you may have real trouble in low dimensions. How does that work out?
But are you referring to the large D expansion?
Yeah, you go to the previous
Yes.
page, right?
Yeah, as far as I know, the large D expansion is asymptotic.
Yeah.
Here, yeah, maybe I should have been a bit more explicit. So these equations are, so the whole calculation that we did was at leading order in the large D expansion.
But when it's asymptotic, how can you be sure that it still works in 2 dimensions and 2 space dimensions?
You're referring to these 2 dimensions?
Yeah. Yeah.
Yeah, no, so what this 2 plus 1 means here is that we take these functions a and p to depend on t, x, and y, so in 3 coordinates in total. So we restrict our dynamics down to 2 plus 1 dimensions. But you're right, in principle, one should go and do the full computation at finite d and see if you get the right result.
But basically 2 plus 1 means you have d minus 2 extra dimensions out there, and you just say nothing is happening out there, we don't force in that direction.
Yes, yeah. But you are right that there is an issue about the if you want the heavy modes that we integrated out, there is the question if they're playing any role in this story. And in order to see that, one really has to be honest and do the finite D calculation. Yeah.
One more question.
Which is complicated.
Yeah, sure, I understand that. It's all fine, but what's your evidence that this 1 over the expansion is asymptotic?
Sorry, Jana.
What is the evidence you have for thinking that the 1 over the expansion is asymptotic?
Oh, this is not my result. I think it was probably by Minuala's group. Yeah. And essentially, they went to very high order in the 1 over D expansion. I think maybe 6 orders, 7 orders. Yeah. And they saw that from a certain point on, the convergence wasn't getting any better if you added more orders.
Okay.
But as far as I know, there was just 1 calculation, and it hasn't been really looked into. So
no,
there is.
That's obvious. I could imagine it's a converging expansion, and that would be beautiful, right? Okay, continue.
Not everything is beautiful in life.
Yeah.
Okay. So these are, yeah.
I'm sorry. Can I also ask a question? You probably said it, but and I missed it probably, and I'm sorry. But these equations are in the first order in time and second order in space. So doesn't this give problems? You said there is, you have to couple all these other modes and so, and that this is not like derivative expansion that is exact. So don't you get problems with causality also in these equations?
So essentially, by taking the large D limit, we land onto something that is non-relativistic, and this is precisely why we have partial 1 derivative in time and 2 derivatives in space. This is non-relativistic.
Yeah. Okay.
So if it was relativistic, yes, I would agree that the powers should match. But once you take the large D limit, you just get something that is non-relativistic.
Oh, okay, thanks.
Christiana, is there a simple way to see why the large D expansion breaks the Poincare group?
When you do the scaling, so you have to scale things in a certain way, and it turns out that things scale differently for the expansion to make sense.
I see.
I don't think it's, yeah.
The black hole breaks the Poincare group.
Sorry, Ben, I couldn't hear you.
The black hole breaks the Poincare group.
Oh, I see.
And if you took Navier-Stokes equations and you then did a large D expansion, which terms would you not get, or which extra terms would you get compared to the equations you have on your slide?
So, I don't know in terms of precise terms, but the point is that if you start with Navier-Stokes equations, you have a certain set of transport coefficients. And if you set a certain number of transport coefficients to 0, then you will land on these equations here. Now, how do you know which transport coefficients to set to 0 and which ones to keep? Well, you have to know how they scale with D. But in order to know that, you need a macroscopic theory. And this is precisely what gravity is giving us. It's giving us a microscopic theory.
Can you be a bit more precise about these transport coefficients? Because at first order, there are only 2 or 3. So it's not like you have...
This is second order hydro. It truncates to second order hydro.
Okay.
Anything else before I continue? Okay, I'll take that as a no. So now I'm actually gonna show you a set of movies that actually Ben made for me. So the first thing to do, given these equations, is just to go and solve them without adding any forcing, trying to see decaying turbulence. Okay. Okay, and this is precisely what Rosali and collaborators did. They studied both decaying turbulence in 2+1 dimensions and 3+1 dimensions, but let me focus on this case here. So they started by a particular kind of initial conditions that was unstable towards turbulence. Namely, they started from the so-called counterflow initial data, which essentially boil down to this. So you take your energy density being constant, you have the momentum in the x direction being 0, and the momentum in the y direction depending on x in this particular way. And having these initial conditions and the equations that I showed on the previous slide, so they went on to solve the system in a variety of ways, always imposing periodic boundary conditions in these coordinates x and y. So they solved the problem on the torus. Okay, and in doing so, they were monitoring the vorticity that is defined in this way, and they were also looking at the power spectrum to see whether or not they would see K41. Okay, and as I'll show in the first video, what they saw was that indeed the system went into a turbulent regime that eventually decayed. And unfortunately, they weren't able to see a clear power law that was consistent with K41. And that was precisely because there was no driving in the system. And Jan asked about the paper by Paul Chesler and Lars Jaffe. And essentially what they did was to do the exact same calculation that I'm describing here, but in 4 Bach dimensions. And they actually arrived to the same conclusion, that they didn't see clear Kolmogorov scaling. Okay, so let me convince you by showing you the actual video. So here at the background, I'm showing the vorticity. This is the initial slide. So what you're seeing is essentially the initial data. So we have these stripes that correspond to fluid going in this direction, and then a bit below in the opposite direction, etc. And then here at the bottom, what we have is the power spectrum, always in a log-log scale. And here you see 2 features appearing. You see this peak. This peak is localized at a particular wave number. That is associated essentially with the width of these stripes. And then you also see just another blob here at smaller values of k. Essentially, this is just some perturbations that we added in the initial conditions just to kick off turbulence. Okay, and then you also see this line here. This line corresponds to k to the minus 5/3. This is the Kolmogorov prediction, and it's just there essentially to guide your eye. So I'll play this twice. The first time focus on the vorticity at the background, and then focus on the power spectrum. Okay, so let's go. So first we see that as soon as I let go, the initial conditions are unstable. So we see the formation of very small vortices. These vortices, as time passes, they merge together to form bigger and bigger vortices. So we see that we have transfer of energy from small scales to larger scales, which is what one would expect from an inverse cascade. Okay. So let me now play this again and just focus on the power spectrum. So as soon as I let go, you see that that peak that we had there just essentially is removed because that was associated with the initial data. And we see a transfer of energy to smaller values of k, as we would expect from an inverse cascade. But we never actually reach this scaling that was predicted by Kolmogorov. And this is precisely because there is no driving in the system. Okay, so this is precisely what we did. So we took the equations that we had before, and we added a forcing term. We added this term by hand, which is typically what people do when in fluid mechanics. And we added it in this particular way in order to produce vorticity, but without actually sourcing the energy density of the system. So the energy, the time evolution of the energy density is the same as before, but the equation for the momentum just picks a term, a forcing term on the right-hand side. And this Fi is constructed in this particular way. So we have a scalar that is F, we take its gradient, and then we dot that with the antisymmetric tensor in 2 dimensions, okay? And then in order to introduce vorticity into the system. But now this F cannot be anything. It has to be compatible with the isotropy hypothesis. So the way we construct it is the following. We pick a scale in momentum space, and then we go and we add all the modes that lie along that circle in momentum space. And we do that with random amplitudes and random phases, and we update all those at every time in the time evolution. Okay. And since we are driving the system, in order to see turbulence, we do not need to consider any special initial conditions. In fact, we can simply start from equilibrium. So these are the initial conditions that we consider: constant energy density and 0 momentum. And just like Rosali and company did, we impose periodic boundary conditions on X and Y. So we solve the problem on the torus. And in order to solve that, we are using 4th order Runge-Kutta time stepping. And for the spatial derivatives, we use 4th order finite differencing. Okay. And this is what we get. So once again, I'm showing the vorticity at the background and the kinetic energy power spectrum in a logarithmic scale at the bottom. And I'll play this twice, just like I did before. Okay. So you saw at the very initial time, probably it wasn't very, yeah. So at initial time, there There is no vorticity in the system because we're starting from equilibrium and there is no power here. And as soon as I let this go, we see the formation of very small vortices. These are the ones that we introduce in the system due to the forcing. And as you see, as time passes, these vortices, they do not merge with each other, but they form structures that move coherently. And if you look very, very closely, you'll see that actually as time passes, these coherent structures become bigger and bigger. And maybe you were able to see that there was, at the very end of the simulations, there was something, just one vortex here and one anti-vortex there, very roughly. So now I'll play this again, and this time focus on the power spectrum. Okay, so what we see is that as soon as I let things go, we have a peak appearing at this scale here. This is precisely where we are driving the system. And if we let it go further, we see that there is an accumulation of power and the formation of an inertial range that extends more and more towards the left. This is what one would expect from an inverse cascade. Okay. Of course, as I tried to convey at the very beginning of the talk, turbulence is all about statistics. And what I'm showing you here is just simply one realization. So you may want to ask, okay, how does the power spectrum look when we do the appropriate statistical averaging? And this is precisely what I'm showing here. This is the power spectrum as a function of k on a logarithmic plot when appropriately averaged over 256 realizations. Okay, and here I'm plotting this power spectrum for 4 different values of the time. In all 4 of them, we see that there is a peak here at the driving scale. This is natural. This is where we are doing work into the system. And we see that as time passes, we get the formation of an inertial range that stretches more and more to the left. Okay, and we see that in all of these cases, the scaling in this inertial range is very much compatible with the k to the minus 5/3 scaling that Kolmogorov predicted. Okay, so this was for the kinetic energy power spectrum. We also looked at the structure functions, and this is the picture when we average over 256 realizations once again. Here I'm plotting the longitudinal structure functions going from n equal to 2 all the way to n equal to 10 as functions of the separation R. Okay, and once again, we see that we have in all these 10 structure functions, we get 9 structure functions, and we get very good agreement with Kolmogorov's prediction. Okay, for over a decade. Okay, so this is the punchline of the calculation that we did for homogeneous and isotropic turbulence. We saw that black holes did exhibit universal behavior that was compatible with Kolmogorov's theory. Okay, now of course you might be a bit worried because we put that that forcing term Fi by hand. So you might be worried that we're not actually solving Einstein equations anymore. So the question that naturally arises is whether it is possible to see turbulence in a fully gravitational description. And this is what I will try to argue in the next couple of slides, and I'm running very late, so I'll try to be quick. So first, in doing so, we do want to have forcing term. And in this case, we will drive the system through the formation of the boundary metric. Now, since the boundary condition problem in ADS is different in this case because we have sources on the boundary, we have to go and repeat the procedure, the large D procedure, in order to obtain the new effective equations in the presence of boundary sources. And this is precisely what we did with Ben and Thomas a few years back. And in particular, when one turns on only the TT component of the boundary metric, these large D effective equations look like this. And in particular, they have the same form as I showed in the previous case. So again, there is no forcing for the function A, but there is a forcing for the function P. But now this force is fixed in terms of these boundary sources. We can't change that. And it's given by the gradient of the source, gamma TT. But unfortunately, this is a gradient of a scalar, so it does not inject vorticity. So we cannot just simply go and repeat the calculation that we did on the previous few slides. But nevertheless, we can still see turbulence in this fully gravitational context. It's just we have to be a bit more imaginative in the calculation that we do. And actually, we weren't that imaginative, I guess, because we essentially did a standard experiment from the fluid perspective. So we started with a fluid in a uniform motion from left to right. And then at some time t equals 0, we quenched this boundary metric source from 0 to a symmetric Gaussian profile at a fixed location. Okay, and essentially the way you should view this is that putting an obstacle in the fluid flow. Okay, and of course this setup is neither homogeneous nor isotropic, so we are not expecting to see K41, but what we do expect to see is to have turbulent wake. So we expect to see the formation of vortices at the back of this object that they're then dragged along the flow. And when we did the calculation, this is precisely what we saw. So once again, here I'm showing the vorticity. The fluid is going from left to right. And at time equal 0, I'll turn on the source roughly here. Okay. And if we do that, this is the picture that we get. So indeed, we see a turbulent wake forming. So there are vortices that are formed at the back of this obstacle that are then dragged by the flow. And given that we are imposing periodic boundary conditions like we did before, eventually these vortices will come back, and that's why this picture looks a bit more complicated. But the punchline here is that one can actually have turbulence in a fully gravitational context. Okay.
Christiana,
yeah.
Just clarification questions. So you basically hear a flow, and then you inject a local fluid flow or something. Is that correct? Right, as if you have injected. How to imagine it? You know what to tell the experiment to see this in a fluid dynamics laboratory. What should they do?
Yeah. So you have a flow. You have a fluid that goes that has a velocity in one direction, going from say left to right, and then at some point you just put an obstacle in the way of that flow. You have a river and you put a stone.
It's like from Carmen.
Yeah,
it's from Carmen in essence. Yeah. Okay. Next question is similar. What should I tell to gravitational people that they should do to a black hole in order to see this in the near horizon of the black hole? What should they do? I mean,
yeah. So essentially, I think I see your question.
Right. So we understand from Carmen in the boundary, but what does it mean in terms of gravitational physics involving real life astrophysical black holes in the
Yes, that's actually a very good question, Jan. Can I postpone it for maybe a slide?
I'm just curious, you know, it's beautiful.
Yeah, no, I will answer it. Okay, so the punchline here is that we can see turbulence from a fully gravitational perspective. Okay, and with this, let me conclude. Essentially, summarize and conclude. So here we studied turbulent black holes with a homogeneous and isotropic forcing that we put by hand. And in order to construct these solutions, we had to go, or we chose to go to the large D expansion, where we got more analytic control over the equations. And it turned out that by solving two equations for two functions, we were actually able to construct the full ADS black brains. And by studying the properties of those black brains, we saw universality that was actually consistent with K41 to a very high degree. That was the second video that I showed you. And the very last one was essentially a fully gravitational computation where we used explicit gravitational sources in order to see a tidally induced turbulent wake. And now let me just very quickly comment on the physical significance of these calculations. So on the one hand, from the point of view of ADS-CFT, these calculations are relevant when one wants to study turbulence at strong coupling, say either at systems related to quark-clone plasma or condensed matter. But they can also be interesting from the purely gravitational perspective, and this is where Jan's question lies. So here, when discussing the gravitational impact of this computation, there are two ways to proceed. One is just to ask questions like, what geometric quantities actually capture turbulence? What's the gravitational origin of the turbulent cascades? What's the difference when you go from 2+1 to 3+1 dimensional turbulence from the gravity perspective? What are the similarities with Aradakis instabilities? And there is a whole story there. And there is another story that is related to whether we might ever be able to actually observe gravitational turbulence experimentally. So the hope is, so in a merger, say LIGO, through the LIGO observations, essentially we have access to a regime that is highly nonlinear. That's when the actual merger takes place. But during, so one might hope to see an imprint of turbulence there. And the reason why that might be the case is because, so if you have an object that is in a laminar flow or in a turbulent flow, the drag force that that object will experience is qualitatively different. So if we have two black holes that are about to merge, if there is turbulence taking place, the plunge dynamics will be affected because the drag force that one of the objects will feel will be different than if laminar. But of course, in order to make any of this more precise, we need to consider finite dimensions. We need to consider spherical horizons instead of planar. Everything that I was talking about here is about black brains, not black holes. And then we also need to go to asymptotically flat space, which is the more conceptually difficult part in the sense that one So in a space-time that is asymptotically flat, you're losing energy both from the horizon and asymptotically. So you would expect turbulence to be much weaker if it's even there. So you need to find ways to amplify that. And one such way is to consider very high spin. So it turns out that this process might actually have an imprint of highly spinning black holes that are merging. Jan, did I answer your question?
An extra question, right? That there is this business that this looks to me quite hairy black hole stuff, right? And there's the no-hair theorem that needs flat asymptotics, right? And there's also saying it's a no-hair theorem. Isn't that no-hair theorem interfering with this when you consider asymptotically flat geometry?
I don't see why it would.
It's just very general, right? That it's sort of this central thing in holography that we have a no-hair theorem and black holes cannot have interesting attitudes, but an entity sitter, there is no such thing as a no-hair theorem, so all these things have hair. And is actually the sort of turbulent horizons, is that hair in this regard, or is this, you know, rather independent of the asymptotics as compared to the usual no-hair business? How is that?
Yeah, okay, so let me try to say something that might or might not help. So in the picture that I was describing in asymptotically flat space, you have a system of two black holes, okay? You have one black hole that is highly spinning, and then you have another one that is about to fall in. Now, this other black hole you can consider as a source. So the no-hair theorems apply when you have a single, well, not necessarily. I don't think they apply in this case.
Yeah, that's basically what I also believe, right? Don't worry about no-hair theorems because it's way too dynamical and there's way too much going on compared to what's addressed in the usual no-hair theorem context. Okay, fine. I'm perfectly happy with it. It's very exciting.
Yeah, so sorry, I overran. So let me leave it here if you have any questions. Oops. Oops.
Could I ask about charged fluids?
We haven't done anything about that.
No, that I understand. But
well,
you could try to reproduce Kolmogorov's arguments for relativistic charged fluids. And then it's not obvious to me that simple dimensional analysis would work, right? Because you have now more skills in your problem.
Sorry, please. I'm just trying to reshare these slides, and I don't seem to be able to do that. Share. Yeah, sorry. You were asking about the scaling argument by Kolmogorov and whether it applies on in the case where there are additional charges in the system, correct?
Yes, that's right.
Yeah. Yeah, no, I guess it wouldn't apply in the sense that you won't just have epsilon, the energy transfer rate. But I don't know if any statements have been made about any other sort of power loss that one could see.
Okay.
Okay, let's thank Christiana for her nice talk. Thank you, Christiana. I think because we have a parallel activity in Holotube for juniors, we may have a few minutes. Can you hear me, Christiana?
Yeah, sorry,
okay.
I overrun.
Oh, no. Thank you very much for your nice talk. And we may have time for a few questions if.
Can I ask one question again? It's Sasha again.
Please, Sasha.
Yeah, Christiana, thanks. Thanks for a very nice talk. So I had some connection problems in between. So maybe you already answered this, but so basically in the large D, you see inverse cascade, which is the same as what you see in 2+1D. Is that right?
Well, I see that because I chose to restrict the dynamics in 2+1 dimensions. You can as well do 3+1 if you want.
In large D.
In large D.
And then you would see cascades, not inverse cascades.
You would see presumably the direct cascade. Now in the large D, Rosali and collaborators did consider turbulence in 3+1, but it was decaying turbulence, so they didn't see the scalings appearing.
Do we know from dimensional analysis what like 4D, 5D, 6D fluids should have?
In the inertial range, it will be k to the minus 5/3.
Okay, okay. So there's no, I mean, so in the large D, there's no, like, I was wondering if there's some new emergent entropy being conserved or something in the large D, that they would be again conserved, or, you know?
Well, I mean, the quick answer is we haven't looked into that. So the entropy is conserved. You see constant, you only see the impact of entropy in 2+1 dimensions in the direct cascade that I chose not to, I chose to ignore.
Okay.
I just don't understand why I can't share my screen. So I wouldn't expect to see.
You are sharing it. I can see your screen.
Oh, can you? Ah. Why didn't you say anything?
Yeah.
Yeah. Sorry. Okay. So this is the argument that says that the power would always be k to the minus 5/3, irrespective of the number of dimensions. And then what was the second part of the question?
Entropy, I was curious.
Yes, yeah. So here there is this direct cascade. So in 2+1 dimensions, at least my understanding is that you have energy being transferred from here, from the forcing scale to smaller values of k, and then you have another quantity that is being transferred to higher values of k. But as far as I understand, that's very special in 2+1 dimensions. I don't know if it would exist in higher, say 4+1.
Okay, all right, thanks.
Christiana, I have also a question. Can I ask?
Yeah.
I think in addition to power law, there is another nice analytic relation or expression, which is the coefficient in front of the 3-point function, firstly found by Kolmogorov, I think, -4/5, something like this. My question is whether this setup, I mean holographic setup for turbulence, is able to reproduce that coefficient precisely or not. Because most of the time when people talk about turbulence in the context of holography, they just found they show that there's some power law, but I haven't heard no one talk about this coefficient.
I'm afraid we didn't check. I'm sorry.
No, my question is, what do you think about that? Is this setup able to do that? My question is this.
Well, given the very high degree of agreement that we had with Kolmogorov scaling, I would say yes. Like standard simulations that claim to have Kolmogorov scaling, they see it in the power spectrum, and they also see it for the first few structure functions but they're never quite able to see it all the way to the 10th longitudinal structure function, as we saw. So, and this very high degree of agreement that we have is essentially because we are not allowing any intermittency, which is usually what takes you away from Kolmogorov phenomenology. So based on that, I would say that in principle, we should be able to see that coefficient.
Yeah. And you mean in the case of a 2-point function of velocity, there is no any effect of intermittency?
You mean S2?
Yes, for S2.
Well, I mean, you see how good the agreement is.
Yeah.
It goes worse as n increases.
Yes. Good. And how about the last slide? I would like to know whether in the case that you show, yes, gravitational. I mean, yes. Is it possible to, for example, look at farther distances in the downstream and see whether there might be some homogeneous region or not? I mean, far from the obstacle. Because naturally, in practical situations, people expect to see, people expect these symmetries, these broken symmetries, to be restored again, and maybe in larger distances in far distances from the obstacle, again, some Power law behavior could be observed.
I don't think so. And I'm basing that on the fact that, well, it's decaying. If you're far from the obstacle, you are not continuously driving the system. You are not populating continuously the cascade. So I would say no.
Okay, your answer is no. Thank you very much.
I think so.
Thank you. So any other question? I think if there is no any question, thank you again, Christiana, and we can end this session at this point. Thank you, and see you all next week. Goodbye.
Bye-bye.
Thanks, Christiana.
Thank you.
Bye.
Thanks. Bye-bye.
Bye-bye. Oh, so I'm the host now?
I think so, yes.
Okay, bye.
I guess now this is...
and I'm still recording.
Okay.
They're awful.
Okay, bye-bye.
Bye-bye.